Good afternoon, dear colleagues. My name is Dmytro. Together with Vyacheslav Kharchenko, we present the concept of intelligent UAV-UGV-SN-based system for monitoring and preventing forest fires. Today, I will talk about motivation and modern solution in the fields of fire monitoring, formulate the goals and objectives of the research, present the system architecture and scenarios of its operation, describe the neural network subsystem and the results of the experiment, as well as summarize the results and outline direction for future research. The results of research is supported by project development of wildfire preparedness and prevention framework for unmanned vehicle platforms, Wildcat, funded by Swedish Institute, Consortium, KTH University Stockholm, Kharkiv, Sakar Ltd, Tallinn. The threat of forest fire is becoming critical due to climate change, prolonged drought and anthropogenic factors. Their number has increased by 13% over the past year. In the realities of hybrid warfare, when there is a risk of shelling, mining and sabotage, even firefighting measures become more complicated as flames can become a means of subversion. Traditional methods of detecting and localizing fires no longer always provided sufficient speed and safety. Therefore, the combination of unmanned aerial vehicle ground robots and distributed sensor networks will allow us to instantly detect fires, accurately localize the fire and predict the development of the situation. The synergy of technology will ensure a proactive approach, reduce environmental, economical, social losses, and increase resilience to crisis challenges. We have now brief reviewed the key research areas in forest fires monitoring, UAVs with thermal images and multispectral cameras for rapid detection of hotspots, energy-efficient sensor networks in hard-to-research areas with reliable data transmission, IE methods for fire spread prediction, and dynamic risk map combustion models that take vegetation, terrain, and weather conditions into account. Automated detection from satellite imagery and integration of UAVs with UGVs for detection and extinguishment. It has been observed that there is a lack of a holistic system that integrates mobile platforms and fixed sensors with real-time neural networks prediction. Our research aims to close this gap. The main objectives is to develop the concept and application scenarios of an integrated system for monitoring and fighting forest fires. Objectives to justify the architecture, generate operation sensors, create neural network technology for data analysis, and conduct an experiment to evaluate clustering. The system architecture will be based on the integration of several components. The sensor networks collect data in real time. Unmanned aerial vehicles perform surveillance, and ground robots are involved in creating fire breaks and firefighting. The control center analyzes the data received, coordinates the actions of all subsystems, and uses neural networks to predict and cluster risk zone. Here is a preliminary table of the key scenarios of system operation from IE forecasting and early detection to autonomous firefighting and forest restoration. These scenarios are the basis that will be detailed and refined during further development and field testing. Here is the architecture of a clustered neural network that will be the heart of our system. The data acquisition subsystem will provide information from distributed sensor and the UAV, which will allow us to cover a large area. Then the pre-processing subsystem will filter, normalize, eliminate anomalies, aggregate and synchronize time series, creating a clean data set for analysis. The next step will be to process the data in the neural network itself and cluster it, which will allow us to identify key patterns such as correlation between humidity, temperature, and gas concentrations, and automatically categorize forest areas by risk level. The result will be a dynamic risk map that will be updated in real time and reflect current threat levels in different areas. The forecasting system will analyze historical and current data to assess the likelihood of fires, which will allow timely preventive measures from moistening areas to installing additional barriers. The key element is automatic learning and adaptation. The networks will constantly update clustering and forecasting algorithms based on new data, ensuring high efficiency in changing conditions. This approach will allow us to quickly identify potential threats and make informed decisions to prevent forest fires. The system will combine data collection, analysis, and rapid response using a multi-level approach to data processing. First, a map containing average temperature, humidity, and other climatic characteristics will be created, which will serve as a basis for assessing the long-term condition of the territory. In parallel, data will be collected in real time using sensors located throughout the territory. These devices will constantly record the current environmental parameters, temperature, humidity, and other important indicators, which will allow timely detection of changes in the situation. After that, a dynamic risk map is created. If a yellow signal appears on it, indicating a potential threat, the system will automatically send a drone for a detailed inspection of the relevant areas. The drone flies to confirm or deny the presence of a hazard, providing additional information through video and photos. If after drone's inspection, the information confirms that the fire has already started or is at an early stage, the system will immediately activate the extinguish mode. At this stage, the neural networks will update the status of the zone on the map, making it in red, signals signaling the need for prompt intervention. The UAV swarm perform initial monitoring of the fire zone and maintains communication with the ground station and UGV units at the zone. At this time, the UGVs begin to actively extinguish the fire and create fire breaks, isolating the fire zone and preventing further spread of the flames. As already mentioned, neural networks will be used to analyze both historical and current data. The input data will be annual climate records and real-time sensor data, and the output will be dynamic risk map. The use of neural networks will allow to quickly process large amounts of information, recognition hidden patterns, and efficiently predict potential threats. The use of clustering will help divide the territory into zones with different levels of risk, which will facilitate the optimal allocation of resources and operational decision making. In the experiment, we use a synthetic set of 12,000 observations on 5 attributes. Risk is categorized into classes: low, medium, and high. Quality assessment sought precision recall and F1 score for each classes, and macro F1. We used precision recall F1 and macro F1 to evaluate the classification quality, precision, the proportion of correct responses for class I, recall ability to find all objects of class I, F1, the balance between precision and recall, macro F1, the average F1 across low, medium, and high risk classes. The experiment's results showed macro F1 is 0.85 for the hybrid model versus 0.81 for pure Q-means. This improves a more balanced and high-risk sensitive classification, which is critically for timely response. Based on the results of the experiment, we propose the following directions to improve the efficiency of the system: data normalizing to reduce variability, comprehensive fire danger index for easily interpretation, threshold detectors to filter out extremely false alarms, incremental learning to adapt to new data, addition of satellite and multispectral data to improve accuracy. These measures will not only improve the accuracy and reliability of risk zone classification, but also reduce the system's response time to real threats. To summarize the results, I will highlight the key achievements of our study: an integrated architecture combined UAV and UGV platforms with a fixed sensor networks was developed. Implementation of hybrid MLP and key means model demonstrated improvement in macro F1 and high sensitivity to high risk areas. Methods to improve quality are proposed: data normalization, complex indicators, and hybrid detectors, which will reduce false positive. The development of systems ready for expansion, integrated satellite data, implementation of incremental learning, and autonomous response scenarios are possible. In the future, we plan to conduct field trials, test the scalability of the system in different climatic conditions, and implement autonomous route planning mechanisms for UAV and UGV. In preparing this paper research, we reviewed key publications on each component of the wildfire monitoring and prevention system. Thank you for your attention. If you have questions or comments, I will be happy to answer and discuss the details, or you can send me a message via email.